Okay, welcome everybody to physics here today. We're going to be studying inelastic collisions, and we have some videos that we're going to be analyzing. And the first video here is this. Okay. Okay, so you were right about that, Meyer. You did see that. You predicted that. You're right. Um, that is what happened. Oh, actually, did they stick? Oh, yeah, they did. I'm sorry. The video started over. So in this collision, we can see that we have an initial momentum that comes just out of this car. And the way that I got, you can't really see this, but there is a photo gate right here, and there's also another photo gate right here. So these velocities come out of that. And so if we're talking about this is called an inelastic collision. In fact, this is called perfectly inelastic. Okay, so this is perfectly inelastic. And the definition of perfectly inelastic means that the two objects stick together and they roll as one object. Okay, so I'll show you how to analyze this here, but keeping in mind what we've already mentioned today, that momentum initially always is equal to momentum final. And the only thing is with this is we're doing just linear collisions. Now, if you think of a collision in real life, it's more than linear. Things are going all over the place. But this is where we have to start to understand what happens here. So we're saying that momentum linearly is going to be conserved, but it really is conserved in all dimensions. Okay, so if we look at this, who can tell me what the initial momentum would be? Well, before that, I'll show you how to write this up. M1 v sub naught 1 plus M2 v sub naught 2 is going to equal M1 v1 plus M2 v2. Okay, so really kind of the hard part of this, the algebra is not that hard, but there are a lot of variables, and you have to keep them straight. So the hardest part usually is the kids, have a hard time understanding the importance of the algebraic signs. Okay, so if we're thinking of the algebraic signs and the importance of them, could somebody tell me what I might be thinking? What am I talking about? What is the importance of an algebraic sign? More specifically, the algebraic signs positive and negative. Okay, thank you very much, Meyer, for answering. Direction is exactly right. Okay, I'm going to call on somebody else now. Jason, can you tell me, can you distinguish between the two directions? And how would you distinguish between them? Since it's linear, we're really only talking two directions. Yeah, so the two directions would be positive and negative. And can you tell me how we actually distinguish between those two? Or how we take out of a real life situation and notate that algebraic. Okay, that's exactly right. So you're saying that it'd be positive if the momentum's going the same way as velocity or something like that, which, that could be positive or negative. But really the important part is the second part that you said, and that's what really is going to help you get the correct numbers with the algebra, is that the negative is the opposite direction as the positive. Okay? So positive and negative are arbitrary, but the important part is that you need to know that they're opposite, 180 degrees different from each other. Okay, so with that said, let's fill in some of these variables. So mass 1, we can call mass 1, I guess we'll just start with this one. We'll call this 1. We'll call this 2. But mass 1 then is 1.5 kilograms. And the velocity here is 0. And then mass 2 would be 0.5. And the velocity here would be, I'll say, what do you want to say, you guys? It's arbitrary. What should we say? negative. I'll call this negative 8. And like I said, it's arbitrary, but kind of by convention, to the left is negative. If you don't know what else to do, you can follow that convention. Now, what did I do at this point? What did I just do? Because I did do something, and it's very important. Can someone, well, let me ask somebody. Okay, Jordan, what was that?
That's the initial momentum.
This side right here is the initial momentum. Okay, could I simplify this right now?
Yeah.
Yeah, because this is 0, so really all I'm going to have is a negative 4 kilogram meters per second. That's my initial momentum. Okay, now there's something even a little bit more simple here that I did that I have to be aware of for the whole rest of the problem. It's what I did when I wrote out this line. I did something that is going to affect me for the whole rest of the problem. And if I don't know what I did here at this point, then I probably will not be successful with my final answer. There's a chance I could. It's kind of 50-50. But can you describe something in here that I did that is, very important? It's simple. Don't think too hard about it maybe, but very, very good. That's exactly right, Casey. The thing is, I did this. I made that negative, which by default makes this direction negative for the entire problem. And I have to follow that convention that I set up for this problem, and I'll get the right answer. If I don't do it, I'm not going to get the right answer. And that is where most of the mistakes come from in all of this math. So if you can concrete that in your head right now, that's an important thing to be conscious of, then you will have a lot less problems here throughout. Okay, so if we just continue to fill in the blanks here, then my mass 1 final, actually these two roll together now, so a good way to signify that would just be m1 plus m2 times the common velocity. And then so if we fill in the masses, we'll see that we have 2 kilograms times our unknown divided by 2, and our velocity here then would be a negative 2 meters per second. As long as I did all my algebra right there, you might want to check it. Do you guys agree with that answer? Okay, so since we all agree, then we can go on to the next situation here. Okay, so this is our second video. Okay, so this is different because we have, 2 momentums in the beginning, whereas before we didn't have 2, we only had 1, and then in the end we had 1. In this case, now we have 2 momentums in the beginning, and then we have 1 momentum in the end. If I can get a volunteer here to help me fill in these pieces, I would appreciate that. I'll just get us started here. Okay, so that was kind of interesting thing that happened there. See that computer glitch? Okay, so what would the first? Okay, Tanner, thanks a lot for explaining that first side, and I like the way that you addressed this right here. We made the 3 negative, which meant that this direction here is actually going to be a negative direction. Okay, so this is kind of a checker too. So in the end, if we get especially when we see the actual event, if we get a number that is the opposite of the sign that it's supposed to be, then we did something wrong with our math. Okay, so then the second side here is less predictable. In fact, the only way that you can solve these problems is by actually having, oh, I guess they stick together, so it is more predictable than I expected. Okay, so Tanner, can you continue and tell me how to fill in the second side here? Okay. Okay, so 1.5 plus 0.5, since they stick together, they have a common velocity. Divide both sides by 2, and we'll find out that our velocity here is, who can do that math real quickly in their head? Stoddard. What do we get on the left side here? So 1.5 divided by 2, 0.75 meters per second. Now, if we follow our algebra, should this be a positive or a negative sign? Is it positive? Okay, so it should be a positive sign, which in this case means it must be going this way. Let's just check that collision again and see if that's the case. And it is the case. Okay, and that's a valid number. Okay, good. So let's look at another one. Okay, we'll take a look at the third video here. See what happens. Okay, what distinguishes between this collision and the other two collisions? This one is, okay, elastic is, we haven't gotten into the hardcore definition of elastic yet, but elastic is when there's a true conservation of kinetic energy. We did talk about it last week, but I haven't expected you to remember that. So if we're hearing sound, is that considered energy? Yeah. That's considered energy. So if that sound is making, you know, the air move and our ears move, then I'd say that it's not in the collision, it's not wrapped up with the vehicles. Do you agree with that? So it would actually not be elastic, but it would be more close to elastic than the other one. This is still called inelastic collision. Okay, that's exactly right. These are not sticking, so they are inelastic, but they're not sticking, and so therefore in the math we'll see that they don't have a common velocity. So we'll put this together, and we have our M1, V sub naught 1. So think of who wants to tell me what to write on this one. Okay, so for the first line, Alyssa, do you want to give us evidences for the first side, the left side of the algebra? What do we have here? Okay, now that's correct. So we could just finish this side and we could say that our momentum here is actually a positive 3 kilogram meters per second. Do you guys agree with that? Okay, so now on this one though, what we needed to do is I needed to have one of the car's velocities after the collision. And what I realized was the velocity 1 of the car was 1.5 meters per second. So if we look at this video again, we said this was 1, said that I slowed down to 1.5 meters per second, still in the same direction. So I would fill it in like this. Okay, so just so we get this on the video, what I did is subtracted 2.25 from both sides to get rid of that. And then we're going to divide that by 0.5. And then we should see our unknown velocity here is 1.5 meters per second. Now, is this positive or negative? Connor, positive or negative on that one? Positive is correct, so we'll just leave it like that. And just to review the video, make sure that we actually did get the right direction, and we did. Okay, so it slowed down by half a meter per second in that collision. Okay. Okay. So for our fourth video here, we'll see something even different. Okay. Logan, can you tell me what the difference is between this one and the other two? Or the other three, actually? Okay, so that after the collision, the velocity of this car changed. Okay, so this brings up a concept question that I have for you, and that is, if this velocity of a car changes. So in other words, if it starts out this way and it has an M, okay, and there's another one here that has no M, and it ends up after the collision having another M, what can we say about this M? Okay, so the answer that I got from Stoddard was M2 plus M3 equals M1. Okay, now can you explain that a little bit more? That is correct.
Because all the momentum will be conserved, so your initial momentum will equal the two momentums.
Okay, so that's very good. So this is my initial momentum. This is my final momentum, okay? And this, in this case, if we look at these m's in their vector quality, if we say that m1 is this, okay, then what would we say about m2 and m3? Jenna? How about m2? Let's just start with m2, and we can look at these pictures like that. What would you say about m2? Okay, well, okay, right, so it's going the opposite way, okay? So, if this is the case with M1 and M2, then what can we say about M3, just with arrows? Okay, that's exactly right, Stoddard, you're right. You said that M3, what'd you say again, will be going in the same direction as M1?
Right, because M1's bigger than M2.
So how much bigger should the vector of M3 be? Would you say?
Equal number, M1 is bigger than M2.
Oh, yeah, so, well, if you look at these parts right here, these two pieces would cancel each other out. What I'd be left over with would be this, which should then equal my initial momentum if everything's conserved. Okay, so let's see how the algebra works out for that. Okay, who wants to help me fill in this first line? Okay, so we filled in those first two lines of algebra, and this was found at the photo gate. It had a velocity of a positive 0.5. And then if we go ahead and finish this algebra here, okay, and just to show you what I did here is I took the product away from this side, which is right here, then divided this side by 1.5, which is right here, and then our final velocity here should be negative, because they're both negative in the numerator, a negative 0.833 meters per second. Let's look at the video and see if that's valid. Do you guys agree that's valid? Okay, so now we're going to do some practice here. We're done with the video for today.